Okie dokie, everyone. Okay, welcome everyone. This is the March edition of the virtual PyData Cambridge Meetup. Today we have one speaker, Leandro Nunes, who is going to speak to us about TVMC, a command line driver for TVM. And afterwards we have time for question, obviously. And then we are trying something new. I had this idea to try out this, to somehow try to recreate the atmosphere of the coffee break or the pizza break that we had during the real meetup. It's an experiment. We will see how it works. So I'm going to post instructions to for everyone who is interested to join sort of like a virtual meeting room on gather.town. So I don't know if anyone is as old as me, you will probably remember these Zelda and Legends of Zelda computer games. So the design will look very much familiar to you. So I'm going to say a little bit more how this works in a few seconds. And also the meetup will be recorded. I hope everybody's okay with that. To everyone who dialed in, you cannot share your video. That's just because this Zoom is set up. But of course, if we read out your questions and that sort of stuff, that part will all be recorded. And of course, the presentation as well. Okay, so a quick few words of introduction. We are PyData Cambridge. We started back in November 2018. We have been pretty consistent with our meetups. Almost every month we had a meetup since 2018, only some few outages or exceptions. And we are usually every last Wednesday of the month. And since COVID and the pandemic, we've been virtual as well. So we is 4 of us. It's Federico, Joris, Leandro, and myself, Ole. And I should say we are all volunteers, so we are all doing this in our spare time. Okay, so just a few words for those of you who don't know what is PyData and what do we actually do, what's behind of this. So PyData is the outreach program of NumFOCUS, and NumFOCUS is a non-profit organization based in the US that looks after and supports open source software. What exactly does that mean? So NumFOCUS gives various ways of supports to a lot of really popular open source projects. So they are focused on the Python ecosystem of projects. So a lot of the typical Python analysis and data science tools are supported by NumFOCUS, but it's not only about Python. They have, as you can see on the slides, support for some Julia packages and other languages as well. So they are about open source. They give a lot of financial support, but also sort of like training to open source developers. And it's in general really a very useful thing. I mean, this is really sort of the piping and the infrastructure that keeps a lot of the data science and also, quite frankly, just the internet work running. So and we, as a PyData meetup, we are part of their outreach program. So we're trying to sort of like convey the message, what NumFOCUS does, and sort of present a little bit what they are doing. And if you think that sounds appealing, please do consider a donation to NumFOCUS. There's a link that you can also find on their website. Because we are part of the NumFOCUS outreach program, we also have a code of conduct. It boils really down to a few common sense words. Be kind to others, do not insult or put down others, and in generally behave professional. Just keep in mind that any sort of like harassment and sexist, racist, or exclusionary jokes and language are not appropriate for PyData. if you feel that something wasn't really going quite right and you want to complain about something that you feel didn't follow this code of conduct, you can first of all contact all of us, the organizers. We are on Meetup and we are on Twitter, but we also have like an external person. That's Leonie Mück. That's our code of conduct response person. So you can speak to her directly if you want to not discuss with the organizers something that you felt violated the conduct. So as promised, something a little bit about Gather. So this is sort of like our virtual meeting room. You don't need to write down the link or take screenshots of it. I'm going to post it in the chat towards the end of the meetup as well, so you can just click on that. So it is, of course, voluntary, but I would really encourage everyone to just check in briefly. It's sort of like a virtual meeting room where we can all get together and we can chat directly through video links. So everyone will be able to share video and share voice. But if you don't want that, you can also just chat via the text function. And it's really, meant to be an informal way to talk to us. If you guys want to talk about the meetup, or if you have ideas for other talks, or just want to, maybe touch base with Leandro and chat a little bit more to him, then that's an option. So we will have like a really, I wasn't sure how many people would join. So I have like a pretty large meeting room. I hope people won't get lost in it. There's also something, if you're sort of like close to a table, then you are entering a private area. And then only people that are standing around the table will hear and see what you are saying. So your video becomes localized. So if you just want to sort of like, I don't know, have like a chat with someone, then and don't want to broadcast it to everyone else, then you can just go to one of these tables. And you have to dial in using a PC. There is no app or anything like that. And of course, our code of conduct applies to this post meetup social as well. So please be respectful and in general just kind to each other in this space. I said already we are all volunteers, but we do have sponsors, and I just wanted to briefly explain what they are doing and how they're supporting us. So our sponsoring organizations support us in various ways, for instance, by paying for the Zoom licenses, to pay for meetup.com. Actually, the gather.com is also paid for by NumFOCUS. So all of these organizations support us in various ways. We are not making any money with that, but they support us in other ways. So if anything that these sponsors are doing interests you, for instance, some of the job opportunities that I'm going to show right now, then please, if you contact these organizations, mention that you saw these information or these job adverts at PyData Cambridge. That really helps us a lot, because then these organizations have the feedback that their program is actually useful, what they are doing here, and their postings are being looked at. So when it comes to ARM, they have a couple of job openings. ARM is a local company based here in Cambridge, UK, but they have offices all over the world. These are, I think, of recs that are only based in Cambridge: principal data engineering, graduate data engineering, a data analyst at the undergraduate level, and senior performance analysis engineer in machine learning. So both volunteers, Federico and Leandro, are working for ARM. So if any of this interests you, or just want to learn a little bit more what the company is doing, please do reach out to them, and they will be very happy to talk to you. Then the Raspberry Pi Foundation used to be our venue sponsor. So when we were still allowed to meet up in real life, they were hosting us, and we are of course indebted for that. And the Raspberry Pi makes these mini computers that are very popular, but they have sort of like an educational outreach program as well. If that interests you, check out their weekly live streams. There's a lot of interesting stuff around digital making happening there. And then Fetch AI is also a local company based here in Cambridge. they are in general into the themes around cryptocurrencies and distributed ledgers, doing lots of very interesting stuff around that. They have published a new sets of stop loss agents that are basically helping users to avoid excessive impermanent loss by automatically withdrawing liquidity from Uniswap and PancakeSwap pools. So if you're generally into this topic of cryptocurrencies, I would encourage you to check this out. There's also a launch of their mainnet coming up on the 31st of March 2021. So if you're that's interested, you have all the links here. I will also post a copy of these slides or a link to these slides on the Meetup page. You'll find all the links here. No need to write things down. And if you think this sounds all pretty cool and interesting, then please check out their job adverts as well. Those are 2 examples. They're looking for someone in marketing and communications and a Python developer. So, and possibly more. So feel free to reach out to them if any of this interests you. And last but not least, the PyData Cambridge chapter, we are always looking for speakers. And we're also looking for sponsors. So if you're interested in giving a talk, or if you're interested in sponsoring, or even both, then please get in touch with us. We are happy to talk about both of them. So we are on Twitter. That's our Twitter handle. We have an email address, email at PyData Cambridge. PyDataCambridge@gmail.com, sorry. So please get in touch. Any other feedback is of course always welcome. And the recordings will be published on the general PyData YouTube channel. So if you want to catch up, you can look there. There are also recordings from previous meetups. And that is it in terms of introduction. I'm going to stop share. I'm going to have a very quick look because I saw some question in the Q&A. Oh, there's one question already. I'm going to answer this live. If there is a certificate of participation and so on, I'll answer this later on. And I hand over to Leandro now. Leandro, the floor is yours.
Okay. Yeah, I'll share my screen. Are you?
I could see the slides very briefly, and then they went away. Yeah, okay. I see the slides now.
Okay. Yes. So yes. Well, as Ole mentioned, my name is Leandro, and I work at ARM, and specifically I work in this project called TVM. And my talk today is about TVMC, a command line driver for TVM. I would like to start actually with an introduction, not only about TVMC, but also I appreciate that not everybody is familiar with TVM. So I will start with a brief introduction about TVM. As this talk is being recorded, I will try to give you also some pointers if you want to check out more about the project and how it works and everything, with some links that I will show during the talk, and you can have a look later on. Now, after this introduction, I am going to run 2 demos to illustrate the workflow using TVMC to compile networks using TVM. And in the end, I will be happy to answer any of your questions. So please use the Q&A box on Zoom to post your questions, and I'll pick them up just after the talk. Now, in a quick introduction about TVM and TVMC, so I'd like to just say and kind of the overall relationship between TVM and TVMC is that TVMC works on top of TVM to offer some of the TVM features via a command line interface. And now this is a good point to give one step back and explain a little bit about what TVM is. So if we go to TVM website, which is tvm.apache.org, you'll be able to see this diagram that illustrates and kind of overall approach on TVM. So on the top, you see all the neural network frameworks we use. So TensorFlow, Keras, CoreML, Onyx, PyTorch, that people use to create their models, create their neural networks. And the objective for those neural networks is to run on top of some hardware. So if you see on the bottom side of the diagram, we see hardware devices and runtimes that people want their models to run. So we have CPUs, we have custom accelerators, GPUs, DSPs, NPUs, and all these devices in which people want to run their models. So what TVM does and the main reason why TVM exists is to bridge the gap between many different input network formats created in many different frameworks to be run on hardwares that want to be supported by many frameworks. So on one side, many models that we want to run on different devices. And for that, TVM bridge those different worlds to make the models portable across devices and make the devices to support many input formats. Now, there are many ways we can use TVM. So TVM offers a Python API that you can use to run your models and compile your models and make some model created on one of these frameworks to run on these target devices. You can also use the C++ API in which you write your C++ program to accomplish that using TVM APIs. So now the idea with TVMC is to offer those user-facing features that people want to use TVM exposed as a tool. So TVMC will get those main features that will accomplish tasks that users want, like compilation. I want to get my model and generate a TVM compiled model so that I can run on my device. And on a different moment, I want to get this compiled model and run on the device. So these are the sorts of features that if we look at TVM as a main framework, TVMC will get some of these features and expose those to users in a simple command line interface. Now, to switch back to my slides, then this raises the question of why do we need a command line driver on a framework that offers many, many features already? So there are three main reasons that we see for that. And the most important one is that for people who are interested in deploying their models and to get in those models and make them do something on actual hardware and want to use TVM, they not always are interested in all these underlying layers of the compiler and the frameworks and internal APIs that you need to know to use TVM in C++ or Python for that matter. The second one is to get a unified and documented interface. So means basically self-contained --help options that you can use to understand what is available to you on that tool. And the third one is that if you start using TVM for many models, you see that some of the boilerplate codes that you need to run are very similar. And what we basically did was to consolidate those sources that use kind of good practices on TVM side to expose those features. So you don't need to create boilerplates over and over for each model that you want to run. Now, TVMC is part of TVM. So if you install TVM as a Python package, you already have TVMC. And once you install it, you have TVMC as a command line. I will just quickly demonstrate that on my terminal here. So in this terminal, I have TVM built and installed. And to do that, I can, at this point, tell you that there is this docs page on TVM website. And you see there is installation. And then you can follow this guide in order to have working TVM installation on your machine. Now, once we have this, we can basically, going back to the terminal, just type TVMC, and we'll be able to use the tool on top of TVM. So we can see already that there are some options, there are some commands that you can run, always documented in the command line interface. So as I mentioned, major features are exposed as subcommands. There are 3 subcommands at the moment. The first one is TVMC compile that we use to compile models from the supported frameworks. We have TVMC run also that allow us to run the model compiled using TVMC compile and generate predictions. And we also have TVMC tune that allow us to perform tuning, which is a way that TVM offers some features for us to do improvements on the model for this to run with better performance on a given target device. So on TVMC compile, what we have is the input is a model that we create on one of the supported frameworks. So the supported frameworks at the moment are Keras, Onyx, PyTorch, TensorFlow, and TF-Lite. There's space here. And what we can do is to use TVM to compile that model for a given target device. So some of these devices, for example, if you are compiling it to run on a device that doesn't have native compilation tools for it, you can also use TVMC to cross-compile it to a target device. So if TVM is not supported on that specific device, you can cross-compile it on a different machine. So you have a model that can just run on that target machine. And as a high-level view of that, what we have is the input model. Then we run TVMC compile, and what we get as an output is a TVM compiled module. Now, the next subcommand is TVMC run. So in TVMC run, the main feature we are exposing from TVM is the ability to get a compiled module and produce predictions with it. So we have the compiled module, we give it some inputs, and then we generate predictions. Another important use of TVMC run is that we can generate profiling data. So we can see for our model, each layer of our model, how much of the time spent on running that model is each of its layers consuming. So we'll see one example of that very soon. So the other important thing is that sometimes if we want to run an TVM, to run this TVM compiled module on a remote machine, we can use something that is exposed by TVM, which is called an RPC tracker, so that we can, from our machine, to remote execute on a different machine. So again, as a high level, what we have is we have the compiled module from previous step. We provide it with some input tensors, TVMC run, and we generate the output tensors for us to check or to interpret somehow. I will show you an example of that later on. The third one is the TVMC tune. So TVMC tune exposes the tuning facilities of TVM. So the tuning process aims to do some performance improvements by finding better configuration parameters. So as in shape sizes, for example, it's something that can be tweaked by TVMC tune. The output of a tuning session in TVM, this is kind of more like TVM jargon. The output of a tuning session is a file in JSON format that contains network using these configurations. The performance in terms of time is this. So it can use this data to perform kind of an optimization loop and try to find better parameters for your network. The tuning can take quite a long time. So, and for that reason, for this talk, I have an example of the outputs, and I will point you to some other resources in which you can check and read more about tuning in this context. Now, as a high-level view, we have, for tuning, we have the input model, and then we run TVMC tune on it, and then what we get as an output is tuning logs, which is that JSON file that correlates operators, parameters, and time results. Now, one thing when implementing such a generic tool like TVMC, one thing that is important to realize is that every different model can be very particular in terms of input shapes and output shapes. So if we are dealing with images, for example, for CNNs, we will need to understand whether that, what's the format of the tensors for that particular network, for that particular framework, for example. And it's the same for the output. So what does a set of outputs really mean in terms of human readable information? So are these classes, and what does these class numbers mean, for example? So for that reason, in TVMC, we use the NPZ format. So NPZ format is, you can read it as a serialized NumPy arrays, which in very simple terms means getting that object that is an array and writing that to a file. So in that way, we can provide actually a generic tool, but it requires from us to pre-process inputs that will go to the model, and also to post-process the outputs of that model in order to extract information that is relevant to us. So it means basically that before running, if we want to generate results for our model using TVMC run, we will need to pre-process the inputs to generate an NPZ file that is accepted in the right shapes by that model. whereas in the outputs, we will also need to do some post-processing to, if we want to read the information that those output tensors are giving us. This format is very well documented. You can read about it on the NumPy website. And I will show an example of a fully working example of how this pre-processing and post-processing thing works. Yes, so exporting into NPZ format can be done in a few lines of code using NumPy. I will show an example of that. Now, this was the introduction of TVM, which is this framework that bridges frameworks as in TensorFlow, PyTorch, Onyx, and others with hardware devices, and in particular also with neural network accelerators. So if you are on the side that is implementing your models, you are interested in this model to run on as many devices as possible. If you are a device vendor, you also want to have good coverage in terms of input frameworks. So TVM is that bridge to connect those different worlds. Now I will start with the practical sessions, and there will be 2 practical sessions in this talk. The first one, I will show you how to compile and run a model using TVMC. So for that, just summarize what we want to achieve with that. So we want to run a simple workflow using TVMC from the model to predictions in our local machine. So we will also, to do that, we will use TVMC compile to start from our input model and generate something that runs on our machine. And then we would have that discussion about pre-processing and post-processing of inputs and outputs to be able to check whether these outputs that my model generated really represent what I want to read from that model. Yes, so there are some documentation about that, official documentation on TVM. If you want to have a look, there is a tutorial called Getting Started with TVM Command Line Driver. And we'll show most of what I'm gonna demonstrate here in practice. So have a look on that one if you want to read more about that. Now, the model we are going to use is the ResNet50 model, which is a model used to classify images. And to compile the model, we will basically run TVMC compile. We'll give it a target, and then the model, and we get as an output is a TVM compiled model. So just switch to my terminal, just clean it up. I pre-downloaded the ResNet model. It is here. And what I'm gonna do is to run TVMC compile -- target LLVM. I will explain this LLVM in a sec. And then we have as the final argument the model here. So while it compiles, it takes a few seconds. And I will explain this LLVM, target LLVM for you. So in this command line, what TVM will do, it will use LLVM, which is a compiler framework, if you're not aware, to generate code that will target the local machine. So in practice, it will compile this as a native library that represents that model. So each operator on that model will be sent to LLVM that will generate code that runs on the local machine. And we can actually look into that code if we say -- dump code LL. we can see that intermediate language that was generated that represents native code that will be used to run our model. So just take a moment. So these are some messages. The messages you see are some messages coming from TVM that we'll see that it doesn't have specific configurations for the specific operators on this. And then we use default implementations. That's all. Now, we have this module.tar, this one, which is our compiled model. And we have also, as we sent that -- dump code, we have the LLVM representation, which is the low-level representation for that particular model. If we look into it, we will see that this is LLVM language. What is it? Page down. So for each of the operators, it will have an implementation that will translate in the local machine to native code. Okay, so that's part one. We start from our Onyx model, which is this one, and we generate a compiled model that is the compiled model, model.tar. Now, the second part, we want to use this ResNet model to identify an image. And switching back to the slides, what we want to do is to use TVMC now, TVMC run to input something to that model and then collect the outputs. So the way that we're going to do it is to run TVMC run. We will input some tensors, and then we'll get as an output tensors from the model that we will then interpret. So that's basically, we'll pass this image, and we want to see later on which predictions this model generated. Now, switching to the terminal, what we want to do, so now comes the time that we discussed about input preprocessing and post-processing. Now, if we see, I pre-created here this ResNet inputs, which is a pre-processing script. So if your model is dealing, for example, with sound, you will need to do different pre-processing. If your model is doing some other classification on images or is reducing blur or something different, you need a different pre-processing script that matches the specific tensors your model expects. So if we see this is a very simple script that uses NumPy and Pill to download an image. So it uses some utilities from TVM, but that's not mandatory. So it will download an image, resize to the size that the model expects, transpose the array the way the model expects, apply this, which is normal process if you are dealing with any ImageNet related network. So it does some normalization. And then the only thing here that is required by TVMC is this line here. That's the NumPy, saves that with some name, and then it will save those tensors on a file. So for any other model that you wanted to connect using ResNet, you would need to do some sort of normalization. And the only thing we have on TVMC is that we expect it to be on an NPZ file. Now, this is basically what this script does. This is the pre-processing that is needed. So what I'm going to do, I'm going to execute this ResNet input, and it will, yeah, so the file was pre-downloaded because I prepared it before but basically it downloaded that image and created that cat.npz. So what we are going to do is to do tvmc run -- input. So we will redirect the outputs to something called predictions.npz, which is basically is a way that TVMC will do the similar process with the outputs and serialize to a file. And then we'll say which model we want, and is, of course, the model we compiled before. So running it is quite fast when compared to compiling it, because it will just get the model and run with the input tensors to generate the outputs. And what we need to do now is to validate the output. So there are some tensors in that file, and what we want to do is to check what they mean. So to do that, I created this script, which is called ResNet output. That's the same if you get ResNet outputs anywhere. You will need to do something similar to this. So basically, it downloads a list of labels, which will translate each class to a value that we can read. So a value that's meaningful to us, rather than having a given code and coded value. It will say this encoded value means dog, this encoded value means chair, this encoded value means cat, and all these classes that are ImageNet classes. Then it will read the file, read predictions.npz, which is the file we produced, and will correlate both. So after it correlates both, it will print the five kind of stronger classes, the 5 highly scored classes in that output. So you can see also that ResNet 50 doesn't offer this softmax, which is a way to calibrate the outputs and translate those output tensors to be linked to labels. And that's something we are doing also in this script. So it's a very small script. Again, if your model deal with voice, if your model deal with different types of inputs, sensors, and all these things, you will need a different post-processing script to extract that information from the model to something that you can read. So what we expect when running this is for this print to print a class with a given code, with a given name, and then the probability with a given number. So that's what we are going to do. So we will use this predictions.npz, which is the file we generated. So we just do Python ResNet output. And then for that particular image that we downloaded, that I had on my slide, it classifies it as a tabby cat, tiger cat, tiger, and so on. So very strong. This one radiator, not very strong. But that these are the 5 more highly scored classes in this particular model for this particular input. Okay, so this is basically us validating the output of our script. And then, well, just to wrap up this demo, we compile the model, we deal with inputs and outputs, and then we generate meaningful information that we can read. But that's basically to validate the model. If we are using this tool to generate predictions, is basically for our own consumption. Now, the second one, very quick, is regarding profiling and tuning. So as I mentioned, we want to collect, very often we want to collect performance information from our models. And to do that, we basically run the same TVMC run. We just add profile to this. Yeah, just takes a few seconds. So it generates with some other debug information and things. But the important bit is this table here. So there is this node name, operations, and time, and other information about that particular layer. So we can see that how the time is spent on each layer of our model, and how sometimes TVM can get two or more different operators and fuse those operators into some custom operators to be used on our network. And then we can see how time is being spent on each one of those. So this is useful in case we are looking for bottlenecks in the model and these sorts of things. We can evaluate all this information when generated via TVM and TVMC using those parameters. Now, there is also, so to enable that, we run with -- profile. And as I mentioned, the tuning, basically we run TVMC tune in a given model, and we generate some tuning logs or tuning records, which is the official name for that particular model. I have one example here that I generated before. So is this file here, tuning records? So if we go to tuning records, you see it's more like out of curiosity, just to show that this will basically generate lots of data with different configurations for operators and performance results that we can then use to improve performance on our model. So that's basically the way this works. You run TVMC tune, and then we use the tuning logs for two reasons. You can use the tuning logs to do more tuning and start with some point that we already run. And we can also use the tuning records to compile the model, which is the end goal. Just switch back to the slides. Now, yes, so using the tuning logs, we can use on TVMC compile, which is the end goal. So TVMC compile, we passed tuning logs with those specific logs. And we can also use them for further training if we pass tuning logs to the TVMC tune command. Now, to wrap up the talk, we discussed about TVMC, which is a command line tool for TVM. I briefly introduced TVM, starting from its main goal, which is to bridge frameworks and hardware platforms. We covered compilation and tuning models. So I didn't cover cross compilation in this one, but I can give you a link to that, which I'm going to do in a moment. We discussed, obviously, the need for input pre and post processing of inputs and outputs. That's a requirement from the models, as we are trying to provide a generic tool with TVMC. And also wanted to say that TVMC is under active development at the moment. So lots of new features in discussion and coming in soon. We use O is implemented on GitHub. So TVM's GitHub is Apache/TVM. You can see PRs. We would be very happy if you go there to report bugs, suggest new features, either on GitHub or on the Discuss platform. So I'm just gonna show you something before to finish. So there is this website, which is called tvmconf.org, which is the last year's TVM conference, which happened December last year. And I just wanted to point to the very long list of recorded talks that you can watch. So basically covering TVM back to back. There is a tutorials day basically here. You can even watch a tutorial on TVMC, which is an expanded version of this talk. So if you got interested, want to learn more, so there is this resource which is very good, tvmconf.org. And I guess with that, I can finish. And happy to answer any questions you might have.
Hey, thank you very much, Leandro. Very nice talk. I have two questions in the Q&A for you. Can you see it them right now, or do you want me to read it out?
I can see them. Yeah.
Okay.
So so the first one, it says, is tuning dependent on particular backends, or is it portable due to the minimal portable runtimes? So it's always important that tuning is done on the same platform that you want to run. So, and the main reason for that is that the minimal portable runtimes that you mentioned in the question, it varies in different platforms. For example, if you have a particular NPU device, with a neural network accelerator device, you might benefit from some optimizations that can be done and some operator fusion that can be done on that particular device that doesn't apply to other devices, like, for example, GPUs that might be, that offer more parallelism or benefit from specific shapes and these sorts of things. So more objectively, yes, tuning is dependent on backends. And it's very important that you run tuning on the, if possible, on the specific target device that you want to optimize for. Now, the second one is, can you give a sense of performance gains of compiling using TVM versus just using the framework's own method of running on traditional hardware? Not something as esoteric like DSP. So there are some benefits you can get from translating it to native code. There is a, I don't have the numbers on top of my mind, but there is, I'll try to paste on a link to a blog post that exemplify some of these comparisons. Then performance gains here, I guess they mean time. And yes, so basically the benefit you get of getting native code rather than going through a runtime or some specific runtime provided by the framework. Yeah, I'll try to paste a link about that one.
Cool. Thank you very much, Leandro.
Mm-hmm.
Are there any more questions? Please use the chat or the Q&A function. Okay. If there are no more questions, then I have a very quick one for Leandro. Leandro, you said very little about yourself and what your involvement with the TVM project is. Do you want to say what you're doing for TVM or what you're working on?
Yes. So yes. So I, as I said, I work at ARM, and we have a team that works on TVM and the kind of all aspects of TVM. And my specific involvement at the moment is to maintain and try to help on TVMC side. I also have some contributions on input frameworks like Keras, for example. Yeah, that's mainly what I'm doing at the moment in the project.
Cool. Sounds very interesting. Okay, everyone. Then if there are no more questions, I'm going to stop the recording